Yeah, am I audible or not? Why no response?
You're audible, sir.
No, then maybe the issue from past. Yeah, Shreyas, can you complete the first property? Check whether this equation satisfies the first property, the above thing.
It will be always greater than 0 because it is mod square. First of all, it is we take mod of all xk's, then square it and add it, so it will, and then we take root, so it will be always positive
Okay.
and equal to 0 if and only if all the xk's are 0. So first is satisfied.
Okay. Next, what is the next property? Hmm?
Scalar multiplication.
Yes, norm of alpha x, that should be equal to mod alpha norm x. Whether that is true here? That alpha will be outside from the summation, like the mod alpha, then that square root alpha square will be outside, then the outside the bracket you will be just having mod alpha. Do you see that? What about the third
Yes,
one?
sir.
What about the third property? Triangle inequality, correct? Triangle, yeah. Do you see whether this norm is satisfied by the triangle inequality? Try to see. You need to start with norm of x plus y, correct? What will this be? This will be equal to summation k equal to 1 to n mod of x k plus y k, the whole square, the whole raised to 1 by 2. What next? Just try to see in the expanded form, then maybe you will realize it. Can you prove this? This is less than equal to, maybe I'll put a question mark. Can you do that or not? This is less than equal to, correct. Can you prove this? Hmm? Maybe I'll just give you this as a homework. You try this. Since it is a easy exercise, you try this. And once you're not able to do, we'll do it. Okay. So this is another norm we are having. We saw 3 norms, correct? What are the 3 norms we have seen till now? Norm 1, norm infinity, and then norm 2. Do you agree? These are the 3 norms we have discussed till now. We have seen. Okay. Now, but we have done it in the space Rn. We have defined in the space Rn. The question is that, can I define the same thing in another space? Something like C01, correct? That is the next question. Can I talk about it? Can I generalize this? Okay. So let me just write the definition. Maybe let me just generalize it. So let X be a non-empty set, and let B of X. This is another notation which I'll be using all the time. Let B of X be the set of all bounded real valued function. Or VF लिखो या you just write it in the full form real valued function. Then norm of f to infinity that is defined as supremum of mod f of x, where x belongs to x. Okay, this is another norm I am defining. So here the space is my b of x, that is set of all bounded real functions. That means if you take any two functions f and g, they are going to be bounded. So why this boundedness is important? Can I only have the set of function? Yes, can I only have the set of function? Why this boundedness is required here? That is the question. Yes, is there anyone who can answer? Why do I require boundedness?
So then only supremum can exist.
Very nice, very nice. Then only I can talk about supremum, correct? That is LUB. Then only I can talk about that. Otherwise, not. So that's why I need boundedness. Now, can you quickly check whether this satisfies all the three properties of a norm? Whether this is a norm or not? Can you just check? Check whether all the three properties are true for this function. Yes. What about the first and second property, Payal? Do you see whether that is satisfied here?
Yes, sir, the properties are satisfied.
What about third property? How will you check?
So norm of f plus g of infinity is equal to supremum of mod of f of x plus g of x.
Correct. What next?
So then we can separate the norm, that is supremum of f of x plus g of x is less than equal.
But, do you know the proof? Can you write the proof? I think I discussed this in the last class. I took a combined lecture of SY and TY. I think you guys were absent, but I have discussed that. We have proved this only.
Yes, sir, we proved it.
Correct? So can I write it? Actually, you proved, I think, equality, correct? But it is okay. I am just using inequality. I am just using less than equal to, which is equal to norm f infinity plus norm g infinity. Is that clear? Yes, is that clear?
Yes, sir.
Good. So what can I say? So this guy is a, you can see this is over b of x. This is a norm over b of x. Instead of Rn, this is over b of x. Is that clear? Actually, we
Yes,
wanted to
sir.
explore this thing. We wanted to explore the norm, whether they are true for other function. I saw that if I am having only set of function, then this norm infinity will not work. Correct? I need bounded function. Similarly, let us see about this. Can I talk about norm of f? One. What do I require here for the function? Just check and tell me. Is boundedness is enough for the function here? Can I talk about the say set?
Continuity, sir.
Why continuity is required here?
Uh, Not continuity. There should be finitely many discontinuities.
Or better, you should. It is better to stick with continuity. That is okay.
Yes, sir.
But why? Why? I just wanted to know why.
Because if function is discontinuous at all points, then there its integration is
Or yeah, simply you should say that every function is not integrable, correct?
yes, sir.
That is the simple as answer. I cannot say that if I'm having f and g, any f and g, whether f is integrable or not, I don't know. If f is any function, so I cannot talk about this right hand side. You see that? So my function should be something which. So what should I take the function? Let me take x as c01 na. Will this work now? If I take my x as c01, can you check? Can you quickly check whether this forms a norm? Can you quickly check whether this forms a norm or not? Hmm?
Yes, sir.
What about triangle inequality? Whether that is true? Something like this. Norm of f plus g of 1 that is equal to 0 to 1 mod of f plus g of t something, and then later on we can use here this is less than equal to 0 to 1 mod f of t plus mod g of t, correct? Then you can separate the integral. This will be 0 to 1 mod f of t dt plus 0 to 1 mod g of t. Is that clear? That is quite easy because we have done this property of mod, so that is not a problem here. Norm f plus norm g, correct? Do you agree?
Yes, sir.
What about this one? We talk about norm now. Norm f2 is remaining, correct? Here also, what do I need about the function? Let me just define norm f2 as say integral 0 to 1 mod f of t the whole square raised to 1 by 2. Yeah. What do I require my x to be? Is only a function or only bounded function is enough? Yes. Is only bounded function is enough here? No, no. I need something else. Again, the same thing as in the previous one. Uh, all the function need not be integrable, correct? There may be some function which are not integrable. So what I need my x to be c01. Do you agree? I need my space to be c01. Is it clear to everyone now?
Sir, so one set can have more than one norms.
Correct. We can have so many different norms. You can define so many norms, correct? Just like in the previous example, addition of two matrix, that will be again a matrix. So can you similarly talk about norms, whether they are norm or not? That will be the next question. Again, that let me call that thing as a tutorial problem. We'll do it. We'll discuss this thing. What about algebra of this? Correct. Let us just learn some few. Do you see the notion of these three norms? That is norm 1, norm infinity, and the norm 2. We have extended to these two over function also. In the case of norm infinity, I need the function to be the bounded function, and I wrote it as supremum of mod f of x. But in the case of norm 1 and norm 2, I need the function to be continuous. Why? Because I'm defining norm as integral. Is that okay?
Yes, sir. Sir, so there is no limit on the number of norms.
Yes, you can have infinitely many norms on any set. There is no limit on that. Good. Okay, if you defined one norm on a metric, correct? Then see, you are having already a metric, and if you define another metric on that, maybe I'll just write it so that you understand it properly. Say, let x comma d be a metric space. Let a subset of x be non-empty. Okay, and let us define x comma y belongs to A such that delta of x comma y is equal to d of xy. Okay, then delta is a metric. And it is called induced metric on the subset A. Why this is called induced metric on the subset A? Yes, what is this delta of xy? It is only taking the value from A. Correct, x and y is belong to A. So I can call it as induced metric on A, on the subset A, if it takes only the element of A. Correct? See, d of xy is a metric over x, correct? Do you see this? Look at the first statement. X comma d is a metric. But if you take this x, if you take only the element of A, then that, say, I am going to restrict this d of xy only to the element. So let me, so this is, say, x, and I'm having A in between. Okay? So if I take the element between A only to compute the norm, to compute the metric, d of xy, then I will call that metric as induced metric on the subset A. Is the definition clear? Yeah, is the definition clear?
Yes, sir. Sir,
Good.
examples.
Example, see, I'm restricting my metric. You can take any example here. Suppose I am having Rn. Rn is my example, and I am restricting it at 0, close interval 0 to 1 raised to something like this. Or you can take it as R2. X is my R2, and let me take my A as 0, 1 cross 0, 1. Correct? Now you take any metric. So say for x I am having a Euclidean metric. Let us take Euclidean matrix. Okay, so I am defining a new metric d of x comma y, which is same as d of xy, but in this case my x and y belongs to A. So all the element x and y are in the set A. So this new metric delta, this new metric is called induced metric on the set A, where d is Euclidean metric, you can call it. Is that clear? I'm just restricting to my lower set actually. I am having a set, I am having a metric defined on it. I am just restricting this set to the some points, and the same metric I am calling it as induced metric, which focus only on that that set, that particular set which I am defining. That's why it is called induced on that subset A. Is that okay?
Yes, sir.
Good. Next, have you proved maximum of two metric is metric? Whether the
Yes,
maximum
sir.
of, yeah, good. And what about minimum? You'll see that minimum is not a metric. I expect some of you to give me a counter example. Give me two metric and check whether their minimum is not a metric. So when the minimum will be a metric? The question will be, if this is not a metric, then what is the case in which the minimum will be matrix? So let me just give you an example. Let D be a metric on X, and you are having say let us define delta of X comma Y that is equal to minimum of 1 comma D of XY. Now do you see, I am not taking minimum of two metric here. I am taking minimum of two elements, minimum of one element and one D of XY. Then I am checking about the whether this delta of XY is metric or not. So I'm just doing show that this delta of X comma Y is metric. Can you just quickly check? I'll give you 2 minutes. Try to show whether this delta of XY is a metric or not. Check whether the first condition is satisfied.
Yes, sir. First is satisfied.
The first condition contains two parts. Huh?
Yes, sir.
Okay, will you just speak
Greater
up?
than 0 and
Greater than 0, why?
because D will be greater than 0.
Correct. And
It
the
is a
another guy
metric,
is one. Good.
and it will be 0 only if X is equal to Y.
Okay. That means if you take this delta of XY is 0, it is minimum of 1 comma something else, correct? But this minimum is 0, that means 1 cannot be 0. So this D of XY should be 0. And if D of XY is 0, so X is equal to Y. Do you agree?
Yes, sir.
What about others? Do you follow that? Neha, Ritika, Payal, do you follow that?
Yes, sir.
Sir, but one cannot zero now.
See, you are having minimum of two people, na? So minimum of people is 0. I know one people is not 0. So I am definitely sure that other people should be 0. One people I am having 1. So 1 is not 0. So that minimum ka value, it should be D of XY. Do you agree?
Yes,
That
sir.
means that D of XY should be 0. So if D of XY should be 0, that means X equal to Y. And it is if and only if you can go back. Check others property. Check other property whether that is true or not.
Sir, second property is true because first we have D of XY equals to D of YX. So
Correct.
minimum of 1 comma D of XY should be equal to minimum of 1 comma D
So
of
you can
YX.
write D of XY as D of YX, then that will be equal to delta of YX. Good. Next. Yes. Take some time, think about it. If any one of you have any idea, then you can say.
Sir, minimum of 1 comma xy is less than or equal to minimum of 1 comma d of xz plus d of yz.
Okay,
Uh,
that the whole thing will be less than, correct?
which, sir?
The minimum of 1 comma d of xy, the whole thing is less than equal to minimum of 1
Yes, sir.
comma, correct, yeah. D of xz plus d of zy. What next?
So now can we split that uh, d of xz plus d of
That's
y?
what I'm asking. Can you do that?
I don't know, sir.
Just think about it. This is also a good thinking exercise for you. You can think here also. Good. So, what, do you understand what is the problem here? What is that you have to think? You have to prove minimum of d of x comma 1 comma d of xy, that is less than equal to minimum of 1 comma d of xz plus minimum of 1 comma d of zy. Correct. You can do it in many part. Either you can do it in the cases also here, but no issue. You try it. Again, this will be a tutorial problem. Remind me, huh? What are the tutorial problem? Remind me about the algebra of metric and this one.
Yes, sir.
Okay. Just 1 second. Hmm. So let us go ahead. Yeah, am I sharing the screen? Can you see the screen?
No, sir.
No, sir.
Okay. Now can you see it?
Yes.
Yeah, actually I need to see the syllabus where whether Young's inequality and Holder inequality is in the syllabus or not. Just 1 second. Do you have syllabus, anyone? It is in website, so I can just quickly check in. I have to see whether I have to take that part or not, because that is also included in the reference book, but I think not in the syllabus. Maybe. Okay. Otherwise, we'll start with open wall and closed wall and everything. See, do you know what is the program code while filling the form? What is the program for code for the mathematics? Something 1200, 1 and 2 or something like that. I don't know.
Sir, for TY.
Yes, for 2 mathematics. You have some photo or something. And just tell me what is the program code. I just wanted to.
Sir, we did not have a program code.
Okay.
Last year's syllabus I have, sir.
No. I actually, why I'm asking about program code. I got to see a PDF file in the website asking about, or it was telling about the number of outsider student of TyBsc. So there was, I think, 4 to 6 people in that, and on the right side, they were mentioned about the program code this. So I just wanted to know about what about mathematics? Uh,
This code for the student is 2505 for the maths.
2505.
Yes, sir.
Okay. Okay. So in the syllabus, I'll share you. Hmm. So let us see what are the things we have completed till now. We have done definition example of metric or R2 Euclidean Rn हो गया. Then Euclid soup and some metric or complex also you should do that. Then space L1, L2 space. What is this L1 and L2? See, whatever I have defined norm, na, if you consider both together, then that will call it L1 space. I'll just write it
Sir,
1 second.
screen is not visible.
Hey, okay. Hmm. Why is showing like you cannot see the screen?
No, sir.
Here it is showing that it is already getting shared.
Sir, you
The
can
screen
stop
is
and
not
then
visible
share
to me.
again.
And here is no option for stop sharing also. It is just showing me it is getting shared. Okay, I will maybe join again. Am I audible? Hello.
Yes, sir.
Yes, sir.
Tell me, can you see the screen?
Yes.
Yeah. See, what are the things we have done? Let us see. Our definition example of metric. These all things are done. Space L1 and L2. I'm just going to define that, and then space CAB, continuous function. Then discrete matrix space. We know that distance metric induced by norm. Yeah. Translational invariant. That is also in the last class we have done by the norm. Then metric surface, product of two metric. We talk about product of two metric. Then yeah, there is no and then equality, holders inequality, and so on. So if you are interested, you can read it there. It is in there. So maybe I'll go with that. Product. Let me just first define what is product metric.
So, sir, in this year topology, we are only doing sets and functions only.
No, actually, now we are defining metric. Then in the next unit, there is something else. Sequence and complete metric space. Do you see? Then compact set.
Yes, sir.
Hmm. What is product metric? Let us know. Let x comma d b1. Let me see. Or yeah, that is okay. If I let x comma d and y comma d be metric spaces, then I'm going to define a new metric. Say d of x1 y1 comma x2 y2. Do you see how the element I'm taking? I'm taking from the cross product x cross y. That is equal to maximum of d of x1 x2 comma d of y1 y2. Okay, defines a metric on the product set. Which product? X cross y, correct? On this set I am defining a metric, and this x cross y is called a product metric. We call the metric on x cross y as product metric. Yeah. Read the definition properly and tell me whether you understand the product metric or not. Would you understand?
Sir, we don't know about the sets X and Y, right?
Why?
Like, if they are joint, disjoint, or the relation between them.
Yeah. There is no relation between x and y like that. X and y are any set. Any set such that the metric is same. The d of xy is same defined on that. Do you see in that maximum I wrote d of x1 x2? So that means the same d I have defined for x1 x2 and the same d I defined for y1 y2. That means same d is going to work for both the x and y. So I have to choose a metric, correct, which works for both. And I am defining a new metric which is on x cross y like this. In short, we can define a maximum of two metrics for the product.
Yes, sir.
Now, can you think the other metric on x cross y coming from original metric x and y? I have given you one metric like this. Can you give me any other metric coming from x and y over the product x cross y? Just like I defined about maximum. Can you give me something else?
Sir, Euclidean method.
So you are going to just subtract them or what?
Under root x2 minus x1 the whole square plus y2 minus y1 the whole square.
Okay, correct, good. So that is again another metric which is defined on x cross y. Yeah, what I am thinking, I'm going to state the inequalities. There are some inequalities that is called Young's inequality, Holder's inequality, and Minkowski inequality. These are the three most important inequality. I don't know why they have not included it in the syllabus, but still I'm just I'm not going to prove that unless I'm going to write it for you so that you at least know that what they are. Okay, if you want, you can read it the proof of these three things. Yeah, one more metric, one more example. Finally, the word metric. Let us relate something with matrix. Let me give a matrix. The space here, my space is MNR. What is MNR? This notation also you should remember. This MNR denote set of all in cross n matrix. Let me call it real matrix. Real matrices, and we define. Let me say A equal to Aij. That is in MNR. Okay. We define. So any vector in Aij will look like what? Or you can write it in terms of vector. With the vector, how will the vector look like? A11, A12, A1n, then A21, A22, like this. Correct? I'm just writing like a trail here. And this will belong to which set? Can somebody tell me? Which will belong to R? How many elements are there?
Cross n mn.
Yeah, n cross n. This is a symmetric matrix, so it will be Rn square. Can I say? Yes.
Yes, sir.
Okay. Actually, in particular, this map is a linear isomorphism. Between M and R and Rn square. Using this linear isomorphism, we define the norm. We define norm A. So we are finding norm of a matrix and we are going to define it as summation the mod of Eij the whole square raised to 1 by 2. Okay, over Ij. Ij का value जो भी हो सकता है हो जाए. We don't care. And you can also write it as norm of E11 and like this ENN. So I am defining a new norm on the matrix. Now the question is that whether this matrix, this norm, first of all, whether it is a norm or not, whether it satisfies all the conditions, and that is quite easy to see here. That is same as your norm 2, correct? That is same as norm 2.
Yes, sir.
Correct. And thus we call it as, we call this M and R as is an NLS. Since it is a norm, so it is NLS, norm linear space. Okay. See, don't worry. You must be thinking, sir, why you are giving so many norms, so many metrics. Later on, when we will be actually using these things, then you'll realize that we have already seen some type of norm and something like that. Now I'm just giving you a glimpse of that. Okay. Now, as promised, let me just write the inequalities for you, or maybe I can, yeah, I'll just write it. These are not included in the syllabus, but it is better if you learn it. The first one is called Young's inequality. Okay, let x and y be non-negative real number let p is greater than 1 and q be defined as 1 upon p plus 1 upon q is equal to 1. That means I am given with p. P is any number greater than 1. And I am given with q is such that 1 upon p plus 1 upon q equal to 1. This holds. Okay. Now we have the following Young's inequality. This is called Young's inequality. We have the following inequality, which is known as Young's inequality. What is that? Xy is less than equal to x raised to p upon p plus y raised to q upon q. and equality holds if and only if x raised to p is same as y raised to p. Have you seen something like this? In particular, by putting some value of p and q, have you seen something? Yes, everyone. Have you seen this inequality somewhere? Look at that. What if I am putting the value of p and q as 2?
But this is that AMGM.
Yeah, it will be similar to MGM. See, first of all, can I put p and q as 2? Whether it is satisfying that condition, 1 upon p plus 1 upon q equal to 1. Yes, because 1 upon 2 plus 1 upon 2, that is 1. So I can put p and q as 2. So if you put p and q as 2, so you'll be having actually xy that is less than equal to x square plus y square upon 2, which is same as your EM-GM inequality. Do you all agree? That the little bit changes you may see is that in the case of EM-GM equality, you can make it. You just substitute x equal to root a, y equal to root b. You'll check, you'll get the same thing. If you put it x equal to root a and y equal to root b, this will be equal to root of ab, and that will be a plus b by 2. Do you agree? You see that?
Yes, sir.
Yeah, so this is actually you can say extended version of your EM-GM inequality. This is called Young's inequality, where xy is less than equal to x raised to p upon p plus y raised to q upon q. Is that clear?
Yes, sir.
Good. Now one more thing is Holder's inequality. I think this color won't be good here. Maybe this one. So let x be r raised to n, and again I'm having one is less than p is less than infinity. So I am defining norm x over p as this: summation I equal to 1 to n mod of xi raised to p the whole raised to 1 upon p. This is what I am defining, and for p equal to infinity, this norm x infinity, I am defining it as maximum of mod xi. You have seen this thing actually, where I is running from 1 to n. Okay. And one more thing, what? For p greater than 1, let q be such that 1 upon p plus 1 upon q equal to 1. Okay. And in the case of for p equal to 1, what will be my q? Take q as infinity. Because in the case here, I am saying this whole thing is p greater than 1. But what about if p is 1? Because my p can be between 1 to infinity now. So I have taken all the three cases. So we have Holder inequality. We have Holder's inequality as like this: summation of summation over I mod of ei bi. This is less than equal to norm of E over P, norm of B over Q. Okay, where E and B belongs to Rn. In the case of R, you can write C here. So it is same as over Cn also. Read it properly. Do you see something like this? Have you seen something? Remember, this norm A is defined like this. This is how it is defined.
Cauchy shorts.
Exactly. Good. You see, left hand side it is seems like inner product. So it is summation dot product. So it is extension of that Cauchy-Schwarz inequality, and the equality hold. Maybe I should write equality holds if and only if C1 mod of xk raised to p is same as C2 mod of yk raised to q. Okay. For some non-zero constant C1 and C2. Yes. So this is called Holder's inequality. Remember this. This is norm P is defined this norm infinity. This is our usual notation. Do you know? Till now, if we were having norm 1, so it was summation like this only. If norm 2, then I was having either 2 and here 1 by 2. 3, then 3, 1 by 3 like this. This is in general I am writing. And norm infinity is maximum. That is we already know. Is that okay? The next thing is Minkowski inequality, which actually I in the beginning I was talking about that. This is key over Minkowski. These are three most famous inequality. I'll maybe request you guys to try proving this or see the proof if you get some time, or you can prepare one presentation or something if you get time. Then you can present in front of SY student. To get some time. सेम पी है जैसा ऊपर बोला हम लोगों ने. एंड सेम नॉर्म जैसे हम लोगों ने डिफाइन किया. What about if this p is 2? Equality occurs when C1 and when there exists C1 and C2 such that C1A is equal to C2B. See, all the three proof follows from the first one. If you prove the first one, Holder's inequality, Young's inequality, then you can prove the Holder's inequality by using Young's inequality. And once you prove the Holder and Young's both, you can use it to prove Minkowski inequality. This is something like that. Okay. One homework for you. In any metric space x comma d, show that mod of d of xz minus d of yz, that is less than equal to d of xy. This is a homework problem for you. And in the case of norm also you can write it in an NLS. So you can take it as E and take it as B. In an NLS, mod of norm of X minus norm of Y, that is less than equal to norm of X minus Y for any two vector X and Y. Is that clear? Can you prove this? You just try it. Seems very easy. Just yeah, D of this is XZ. So maybe from the next class we can start with open ball, open set, closed ball, closed set. Okay. So once you have defined open ball, open set, then we'll come to about continuity. We'll come to about sequence and so on. So if you observe, we are doing everything from the start. But here the notion is not only Rn or not only R or R2. Here it may be anything. It is here in the case we are taking metric space. That's it. So what is metric space? We are define a metric on that space. That's why it is called metric space. So here we are defining everything in the notion of metric space. Is that clear?
Yes, sir.
So you have understood this metric concept and that a norm concept. If these two concept is clear to you, and we'll do the tutorial problem, huh? We'll do that. And once these two things are clear, then that means we can now go ahead. We can talk about continuity. You can talk about uniform continuity. You can talk about so many things actually. Once you are clear with this, okay. And the definition will be same. I'm going to ask you in the next lecture. I'm going to ask about what is the definition of open set, closed set. We have done it for R2, R3 in your TyBsc multivariable calculus 1. We have done the definition of sequences in Rn. Here also everything is going to be same, but at the place of mod I'll be having D. There we were having mod because we were in Rn or R. Here we will be in metric. A metric will be defined for that. Okay.
Yes, sir.
Good. So maybe we can stop now. We'll continue in the next class.